Welcome back to Chem 4300. In this video, we're going to continue the topic of chemical kinetics. And now we're going to look at ways that you can experimentally measure reaction rate orders. Now, one of our goals will be to measure the rate constants for a reaction. But before we can do that, we need to know what the actual rate law is that has this corresponding rate constant in it. So what we're after here is we want to know for each of the species involved in the reaction, what are the exponents here, the orders or the partial orders for each one of these species present in the reaction. And we're going to look at three different approaches here. One is called the half-life method, another one's called the differential initial rate method, and then we'll build on that one to form what's called the isolation method. Now, let's go to the half-life method. And you remember before that half-life was the time it takes for a species to be reduced by a factor of 2. If we took a reaction rate that was of this form, where there was only one species involved, then we could take that rate and we can derive an expression that looks like this. I'll leave this as an exercise for you to do. But what's most important is that the log of that half-life will vary linearly with the initial concentration with a slope that's equal to 1 minus n, where n is the order for A in this reaction. And then we have an intercept here, which also involves the order and the rate constant. So this equation gives us sort of a strategy, an algorithm for trying to figure out what the order is for A. And I'll write it down in bullet points here, but then we'll look at an example. So the first thing you're going to do is you're going to measure A as a function of time and plot that. Then you're going to look at the A value at a given point in time and find out when it drops to half and find out what the corresponding half-life is. You do that with another concentration of A, repeat. You do this multiple times. You end up with a list of half-lives associated with initial concentrations. If you plot the log of those half-lives versus the log of the initial concentration, then the slope will give you 1 minus n, and then you'll have the order. All right, that might be kind of tricky to follow. Let's look at a graph of how that works. So here's a concentration of A as a function of time, and I'm looking at a second order reaction here. So we know n will be equal to 2 in this case. Here is the exponential decay of the concentration of A. So maybe I measured this in the lab, and I start out with my initial concentration, say at time 0 of A, and I look on the plot and I find out where from 100 I've dropped down by a factor of 2. That would be 50. I go over here and say when the concentration is at 50, it took here 0.1 minutes to go from 100 to 50. So that half-life is associated with A initially being 100. So next I'll go down my plot and I'll say, well, let's start here at 80. Okay, a little later my concentration was 80. Let's say that that was my initial concentration. Well, if I go over and down, I find that 80 drops to 40 at a time that's 0.125 minutes. So associated with initial concentration of 80, I have a half-life of 0.125 minutes. Similarly, if I started with 60 and say that that was my initial time, dropping to 30 and going over, I find a half-life of 0.167 minutes. So now I have 3 half-lives for 3 initial concentrations. If I plot a log scale of both of those, log of half-life versus log of those initial concentrations, I will get points that will fall on a line, and that slope will be 1 minus n. And so for a second order reaction rate, we expect that slope to be minus 1. But working backwards from the slope, you can get whatever n is, whether it's 0, 1, 2, 3, or whatever. Okay, that's called the half-life method. Now, another approach is what's called the differential or initial rate method, is simply to go back and take this expression that we had before and take the log of both sides, and you see that if you plotted the log of the rate, then versus the log of the concentration, then the slope would be equal to the order. So, well, this concentration here is not going to vary in a way that, in the same way at different times. So what we're going to do is we're going to look at, say, again, take my example that I had before, is, let's say I have a decay for A and I start out with an initial concentration of 100. If I look at the initial slope here for a concentration of 100, then I get a value of 1,000 moles per liter second. If I move down to another initial concentration, say 80, then the initial slope is only 640. If I go to initial concentration of 60, it drops to 360. And if I go to 40 initial concentration, then the initial slope is 160. So now I have, for these initial concentrations, I have the rate, the initial rate. So if I plot the log of the rate versus the log of the concentration, then I'll get a line here, and the slope of this line is going to give me the end value for that reaction. Okay, so in this case, this was a second order case, so this has a slope of 2. Okay. Now, what do you do if you have more than just one species present? So we may have a rate that involves many species. So what you're going to do is you're just going to vary A and hold the other concentrations, other species concentrations constant, and then repeat that process with the other reactant. So this is what's called the isolation method. So if you have some reaction that involves a lot of different species, then what you do is, if you want to focus on A, then you make the concentration of A much less than all of the other species. So you make the other species concentrations very high, so as the reaction proceeds, their drop from a sort of percentage-wise is much smaller than the drop of A. So then you write the reaction like this, where A is the one that you're focusing on, and these are the ones that are set to a very high concentration. You can group them together like this, and we'll call that K prime for the rate constant, and then we'll work on, under these conditions, working out the order for A using the initial rate method in the previous slide. Then we can then just sort of flip over, maybe switch over and make B the one that's low concentration, put A at high concentrations along with the others, rearrange this, and repeat this approach. And that will also then work your way through each one of these species to get their partial orders. Okay. So that's it for this video. And the next, we'll look at how we can predict reaction orders.